The lecture topic is heat generation. A medium through which heat is conducted may involve the conversion of electrical, nuclear or chemical energy into heat or thermal energy. In heat conduction analysis, such conversion processes are characterized as heat generation. For example, the temperature of a resistance wire rises rapidly when electric current passes through it as a result of the electrical energy being converted to heat at a rate of I square R, where I is the current and R is the electrical resistance of the wire. A safe and effective removal of this heat away from the sites of heat generation is the subject of electronics cooling, which is one of the modern application areas of heat transfer. Likewise, a large amount of heat is generated in the fuel elements of nuclear reactors as a result of nuclear fission that serves as the heat source for the nuclear power plants. The natural disintegration of radioactive elements in nuclear waste or other radioactive material also results in the generation of heat through the body. The heat generated in the sun as a result of the fusion of hydrogen into helium makes the sun as a large nuclear reactor that supplies heat to the earth. Another source of heat generation in a medium is exothermic chemical reactions that may occur throughout the medium. The chemical reaction in this case serves as a heat source for the medium. In the case of endothermic reactions, however, heat is absorbed instead of being released during reaction, and thus the chemical reaction serves as a heat sink. The heat generation term becomes a negative quantity in this case. Often, it is also convenient to model the absorption of radiation, such as solar energy or gamma rays, as heat generation when these rays penetrate deep into the body while being absorbed gradually. For example, the absorption of solar energy in large bodies of water can be treated as heat generation throughout the water at a rate equal to the rate of absorption, which varies with the depth. But the absorption of solar energy by an opaque body occurs within a few microns of the surface, and the solar energy that penetrates into the medium in this case can be treated as specified heat flux on the surface. Note that heat generation is a volumetric phenomenon, that is, it occurs throughout the body of a medium. Therefore, the rate of heat generation is a medium is usually specified per unit volume and is measured by G, whose unit is watt per meter cube. The rate of heat generation in a medium may vary with time as well as position within the medium. When the variation of heat generation with the position is known, the total rate of heat generation in a medium of volume V can be determined from capital G equal to integral of small g into dV. In the special case of uniform heat generation, as in the case of electric resistance heating throughout a homogeneous material, the relation in equation reduces to G equal to capital G equal to small g into V, where G is the constant rate of heat generation per unit volume. And in a problem of heat gain by a refrigerator is, in order to size the compressor of a new refrigerator, it is desired to determine the rate of heat transfer from the kitchen air into the refrigerator space through the walls, door and the top and bottom section of the refrigerator. The heat transfer process from the kitchen air to the refrigerator space is transient in nature, since the thermal conditions in the kitchen and the refrigerator in general change the time. However, we would analyze the problem as a steady state heat transfer problem under the most transmitted conditions such as the lowest thermostat settings for the refrigerator space.